are we're a multidisciplinary consultancy, so we do MEP design, architecture, interior, and sustainability, commissioning management. But we also do work on existing buildings, and we employ actually energy modeling on both existing buildings and for new construction. And we're going to see how this is done in buildings, whether they're existing or new. I'm going to switch off my camera just in case someone does not have enough bandwidth. All right, so what is energy modeling? Energy modeling is a process used to estimate the energy consumption of a building, typically on an annual basis, especially for when we talk about residential commercial buildings. It involves simulating how energy is consumed, produced, and transferred within a building, considering factors like building design, geometry, materials, layout, occupant behavior, systems and equipment, and environmental conditions like climate and weather. When it comes to energy modeling approach, we would have mostly two, let's say, main methods. One is data-driven modeling. So if we have, especially an existing building, we could look at existing building data consumption, and we would look at some variables. We call them independent variables, and we could try to relate those variables with the consumption. So for example, we could look at a typical commercial building in Dubai. In most cases, you will see that the energy consumption is driven by weather. So as the temperature increases, the consumption of the building in terms of energy would increase. And that is typical if the building has like its own chillers. If it has district cooling, then you'd look at the district cooling bill and you'd see that as the temperature outside would increase, as the enthalpy would increase, so will the energy consumption. You can build this model, typically a one or multiple variables. Linear model, we try to get to linear modeling when we do data-driven modeling. It could be, if you look at chillers in particular, it might be not to the order of one, but and it could be multiple variables as well. But for buildings, we normally go with linear regression, and it would involve one or multiple variables. One prominent one would be weather. That's not the what we're discussing today. What we're discussing today is the physics-based forward modeling, which is the focus of this presentation. These are simplified models describing first principles. And when I say simplified, I don't mean they're simple, but I'm saying that simplify the first principles engineering, such as heat, trend, mass transfer. So we would have these equations, and we try to kind of solve these equations. We have the structure or the envelope of the building, we have the radiation coming from the sun, we have the heat conduction, convection, so on and so forth. We're trying to figure out how is that being used into the building, or how does it absorb into the building? How does that become a load, and how does that become electrical load, for example, on our chillers or in our fans and our pumps? Comparing the physics-based forward modeling, like I said, and the data-driven modeling, or that, let's say, when we do regression analysis, we would have 1, 2, 3, maybe 4 independent variables. But in the physics-based forward modeling, we would need a lot of different inputs. So we need to get a lot of information about the building, put that into our energy modeling software in order to figure out what is the consumption for different components, as well as for the whole building. For example, we would need to do an energy model to comply with, let's say, the first credit for the, I mean, we don't need to, there are other methods, but if we want to get a lot of points or more points, we would go with energy modeling to prove that our design is better than, let's say, the baseline that is set by ASHRAE standard 90.1. So the forward modeling predicts building energy use by describing physical systems, equipment, and operating conditions. Key inputs would be the geometry, location, materials, and schedules. HVAC systems, we need to put the equipment type, the operating schedule, the plant equipment efficiency, so on and so forth. And then the purpose would be to predict peak and energy use. Now, in our region, peak is not as important at the moment from the tariff point of view. So if you look at your tariff, we don't pay for peak energy. So we don't get, let's say, compared to the US or Europe, where you would find in some states in the US would be maybe $10 per kilowatt per month. So if we have, let's say, 1,000 kW as our peak power during that month, we'd paying 1,000 times 10. That's $10,000 for that specific month. So we don't have at the moment any peak, but we would need to uh, do that for other reasons, but not for the tariff. So we would normally focus on the energy use because this is what the tariff is at the moment. So we pay for a kilowatt hour. So what is the consumption during that particular month, multiplied by that specific tariff, and we get the consumption of or how much we would need to pay for that specific month. So it's grounded in engineering principles, the physics-based modeling, and is widely acceptable in professional design. It has its own limitations. So we need to understand what kind of software we have and what is the task we're trying to do, how certain we need to be. And there's a famous saying that all models are wrong. We never will have a perfectly done model. It will always have some uncertainties. We're going to talk maybe a little bit on at the end of the presentation. Maybe I'll just mention some couple of uncertainty issues we would find when we're doing energy modeling. So what are the steps in physics-based energy simulation? We're focusing on buildings here, commercial buildings, not industrial. First, we start with the space load calculation, and I'm sure most of you have done some kind of energy, some kind of cooling load or heating load calculations. So this is the energy needed to maintain thermal. I wouldn't say thermal comfort, just to be a little bit make it simple. We're saying thermal comfort, but it's basically to get to a certain temperature and maybe humidity. It doesn't mean that it will confirm thermal comfort because we might be, we're not designing the building when we're doing energy modeling. There's someone doing the mechanical design. As an energy modeler, I'm not designing the building. I could be the same person doing both, but if I'm doing the energy model, I'm just assuming that I'm going to have probably that temperature. I mean, the software will calculate that, but it doesn't mean that I will get thermal comfort. There's another, let's say, method to look at. Maybe we'll look at that at the end of the presentation. What is the method to, let's say, do thermal comfort modeling? That's something else. But what is the energy to maintain a certain temperature and a certain humidity level? That's basically more accurate. We consider the temperature, like indoor, outdoor, humidity levels, indoor and outdoor, solar effects, radiation, internal gains, and infiltration. So any kind of loads that would affect my consumption would be needed to be considered. Then from that, we get to the equipment. So what is the energy required for the fans, pumps, piping systems? I mean, that water, let's say chill water is moving through the piping system, that's going to have some friction losses, and this will tell us how much the pump will be using, and that's going to be done on an hourly basis. We end up with an hourly simulation. We know on every hour how much that pump is using, and in total, what is the building is using. And then we would simulate energy distribution systems like AHUs, fan coil units, mostly to get the fan power consumption and what is the consumption of the cooling coil. And then from that cooling coil to the pump, and then from that pump to the chiller, which is the primary equipment loads, and what is the energy required from the chillers, for example. So we have this load distributed by this pump. Now that chiller needs to reject that heat and would need to kind of convey some cooling. To convey that cooling on an hourly basis, what is the consumption for each hour? And that depends also on many other factors. It does consider equipment efficiencies, spark plug characteristics. So it's very, very important that we get the right information into the model. So if I have a chiller from that manufacturer, from this manufacturer, I need to get like a performance map because the chiller is not like lighting. It's not just one point of entry. We need to look at the whole part load condition. What would happen if the chiller was running at 30% load and the outdoor temperature is 45 degrees C and it's an air-cooled chiller? What is that kilowatt per ton? What is that COP? So I need to build that performance map and make sure I would use that in my software. Now the software would have some typical, let's say, curves for the different equipment. It would be okay probably to use for fans, maybe pumps, but for chillers in particular, you'd need to get a performance map from the supplier. And that happens by asking them for different points. So I would ask for different outdoor temperatures for an air-cooled chiller, for different load factors on the chiller, and typically speaking, the supply temperature from the chiller itself would be constant throughout the year, unless you're doing some kind of increase of temperature during winter. Then you need to also ask for that map on different supply temperatures or supply chilled water temperature from the chiller itself. So you need to be as accurate as possible. You need to put as accurate information that will be used in that site. There are many software that are available. This is just showing a few of them. So we have IES. This is software that we use in our office. There's also Design Builder, which is good. This running based on the Energy Plus engine, which is a very powerful engine developed by the U.S. Department of Energy. There's eQuest, which is running on an older engine from DOE with the same name, DOE. There's a standard from ASHRAE, that's standard 140, which tells us a way to test these software. So if you're getting a software, make sure that it has done the test as per 140 and does comply with that, which is simply just comparing the results of that software with some established software that are out there. And it is being updated. So there's a new one that's been published last, well, 2 years ago now, well, less than 2 years, but it keeps on adding some requirements to make sure that the tests kind of look at all elements of energy modeling. Some more software that are available. So we have the engines DOE for eQuest, for example. There's 2.1, 2.2, and 2.3. There's Energy Plus, which runs a lot of the newer, let's say, software. There's HAP from Carrier. Well, Carrier actually have both. There's one that's running Energy Plus, and there's one just using their own engine. And there's Apache that is for IES, and there's Transys, which is another powerful software that I've used before. There's a full list on the IBPSA website. If you want to look at the different software, they do have a list of software, and they kind of give some background on each software. So where can we use energy modeling? We could use it to do a better design, more efficient design. So it helps us make design decisions. I could have 50 different ways to build the building in terms of envelope, in terms of these type of air conditioning. I'm going to go with DX. I'm going to go with inverted DX. I'm going to go with VRF. I'm going to go with air-cooled chillers, water-cooled chillers, district cooling. Which one would be the best? And we're not saying the energy modeling will give you the answer which one is the best, because there are a lot of different factors that need to be taken into account, like cost, like space availability, like thermal comfort, many other aesthetics as well. And the energy modeling software will tell us how much that system would use, and you could compare different systems together and help you and will guide you into finding the right solution for your building or for your system. So it helps us in designing more efficient energy or more efficient buildings from an energy point of view by optimizing the envelope, HVAC, lighting, and other systems. So if I'm doing a building in Dubai, I have the Dubai building code, which says that the U value should be such and such. If I want to go to the easy way, I just use whatever is in the code and tell the client, look, this is what the code requires. And some clients might say, well, what if we go do better than the code? What is the payback period? How much gain would I get? And how many years I need to uh, get my money back? What is the IRR of that option? So in order to answer these questions, then we could say, well, instead of the 0.57 U value, if I use a 0.4, now there's obviously an increase of cost in terms of the installation, but there will be a decrease of cost because now I have smaller equipment on air conditioning, and I have lower energy consumption. And let's see what is that payback period. So the energy modeling, again, will not give us all the answer, will give us the part of the energy. It's not going to give us the cost of the increased installation or the cost of the reduced capacity of the air conditioning units. That's something we need to check on our own, but it will tell us what is the energy consumption, help us make that decision. It will identify opportunities to reduce energy consumption, operational costs, like I just mentioned. And some clients would also want to know what is their consumption. If they build that building as per that design, what was their projected consumption? How much they're going to be putting into the utility bills? And that's help them in foreseeing what's going to happen and put the budget for the operation. So that's also beneficial from that point of view. Compliance with the rating systems. So if you're doing any green building rating systems like LEED, Istidama, these would normally use energy modeling. to show our building, how much is going to be using in terms of energy versus the um, baseline. And the baseline typically would follow ASHA 90.1 Appendix G. And for lead, it was always using the cost comparison. The latest version of 90.1, there are other options. We could look at source energy. We could also look at the emissions. So that's another way to look at it, not just cost, but historically it was always cost. It's the data, for example, that would compare just the energy consumption, not the cost of energy. So yeah, these are the kind of where energy modeling would help us when we're doing some rating systems. Also, the ASHRAE building EQ would use energy modeling if you're doing a design phase. We're going to use it for energy retrofit. So if you have an existing building, I could model the building. It's a little bit more complicated, I would say, and more challenging because with the green building rating systems, I'll be honest with you, at the end of the day, you're going to send this model. It will go and someone will review it, sitting probably in another country, and they might not have all that information. Like they won't go into every drawing of the design to look that your inputs are correct or not. They're going to do some sanity checks, some checks to, and which makes sense, right? They're not going to be able to put 1 month and look at all the drawings and do that. So they're going to do some sanity checks, look at the inputs, look at the outputs, and figure out if it makes sense or does not make sense. So they don't want to go into details of the details. And there's nothing to compare to. There's not like some energy bills we can compare to because that building has not been built yet. When it comes to the energy retrofit projects, this is where you actually do have information from that building, whether it's from local meters, whether it's from the utility meters, and you need to um, compare your results with the utility meter results and any available meters on site to confirm that the model has been calibrated, which make it more challenging because now you can compare to something and it's not just the results of the model. These results need to be compared and confirmed that they are close enough to call that model calibrated. Without having that calibrated model, we can move to the next stage, which is looking at changes within the building, where we could change the consumption. We could or sorry, we could let's say change the chillers. We could change the sequence of operation of certain equipment, or change the equipment themselves, or the schedules, and see what kind of savings we'd have. So we'd need that calibrated model first. Then we move into the doing the energy modeling of the energy conservation measures, energy efficiency measures. Some people call it energy saving opportunities, and then find out what kind of savings we'd get. Now, moving on to digital twins, this is something that we're looking at, and a lot of others are too. And the idea is to have this live model where you could do some changes on the model and it could, tell us how to run the building better. I'd say we're still a bit not 100% there with digital twins, but we're getting there. Now, another an important standard would be ASHRAE Standard 209, which has been published to help designs and using energy modeling for design. So the scope is it applies to new buildings or major renovation, uh, and it uses energy simulation during the design process. So the standard is not applied to single family houses that are smaller than 3 stories. So it's mostly for commercial or large, let's say, buildings. And the idea here is to help designers to understand what kind of effort is required for every stage. So you can see here that it shows that we have the simple box modeling. When we don't have much information, what can we do? We can do some simple box modeling to guide the architect, to guide the designers, guide the client on maybe what is the best orientation. Then we go into the conceptual design modeling, load reduction modeling, HVAC selection modeling. And this is something I see a lot in the market. There would be someone doing a cooling load calculation and someone else doing the energy model. And I'm not sure why the duplication of efforts and why it's not just one model used for both. So that's the recommendation, at least from my side. Then you go into design refinement, design integration, optimization, and then energy simulation, added value engineering. So let's say you got to the point where the contractor now is on board or being awarded, or right before that, and it's just some value engineering, and you need to check as the energy modeler what are the what is the effect of that energy change because of the value engineering. Let's say they come and say, well, we don't want to put VFDs on all the chillers. We want to put only on the first two or only on two chillers because these are the ones that are going to be subjected to partial loads. So if that's a change in design, we need to go back to the model, change that, see what is the effect of that value engineering to see if it makes sense or not to change it. So we would, use energy modeling from the start. That's the recommendation of the standard. The earlier you do the energy model or the energy modeling, you would understand the effect of different things and you could guide the design accordingly. I see a lot of projects where the energy model is being done at the end of detailed design just to figure out how much points we're making. So not a good practice. In my opinion, we should do the energy modeling early on. So simple box modeling, the purpose would be distribution of energy by end use and demand characteristics that affect building conceptual design. So we just try to figure out if we change the orientation, for example, what would be the result. Then the concept design modeling, that would be energy improvements related to buildings form architecture as well, like U values, so on and so forth. And then load reduction modeling help us in strategies to reduce the annual energy use and heating and peak cooling loads through different, let's say, energy conservation measures or energy efficiency measures. Should be completed prior to the final selection of the HVAC system. Then we do the HVAC system modeling, where again we would always look at the energy usage per component and also for the whole. And then that is normally done to help us and select the equipment. And then we do a design refinement. So as you see here, the amount of changes we can make would be drastically reduce as we move on. Like we cannot come at the energy, at the value engineering stage and say, well, yeah, we had air cooled chillers, it's better to go with water cooled chillers. That's not going to be acceptable because you need to go back to kind of square one and change the whole design, which is not feasible at that point in time. But at the conceptual design modeling, I remember I was working on a mall here in Dubai, and the initial concept was for the air cooled chillers. Then we kind of advised the consultant to move towards, at the time was working as a client rep, and we advised the consultant to move into water cooled chillers because the load changed from 3,000 tons to 8,000 tons. Now we could have done that easily at that point in time because it's just concept stage. But if it was detailed design, we'd already done with the tender documents, it's going to be very hard to go back because it's not the HVAC only they're going to change. It's even the architectural, the electrical, everything is going to be changing in that particular building. Construction operations modeling cycles. This is when becomes crucial to figure out the model versus reality and how we need to calibrate it. So we need to use the most updated drawings. So as design energy performance, that's basically construction drawings. Then change orders, any change orders that were done, we update that accordingly. And then the as built, exactly how it was built. And that's going to be the final one. Then the post occupancy cycle, where we actually now have the bills, have the occupancy, and then we would do these typically 12 months calibration, run the model, look at the energy data from the utility meters. Maybe we need to do some measurements to figure out some of the components and update that into the model. So now the results from the model and the actual energy consumption is very similar. That's going to be called a calibrated model. So design phase, then we go into construction, which is simply just updating the model as what happened during negotiation with the contractor, and then what actually happened during the site execution, and what the as-built would be. The as-built model would be as per what was built. And then the post-occupancy would be probably after 12 months, and you have now 12 utility bill months, and then you calibrate the model to show so that the model results would be similar to what the bills are showing. So what are the energy modeling? What is the energy modeling process? What are the required data? I said before, it's going to be a lot of data that is required. So we need the architectural drawings to be able to build the model as like the shell. And we need the weather file. Where are we? In which city? Are we in Dubai? Are we in Abu Dhabi? Are we in I don't know, Jamaica. So we need to get that weather file that would be representative of that place. And typically we would use TMY, typical year meteorological data, which will be retrieved from um, weather stations, and they're typically over 15 or 20 years. And make sure that you understand which file version you're using and what years does that file represent, because some of them would end at a certain year that maybe already 15 years ago or 20 years ago. So you need to use kind of the latest ones. And these are not used for peak load calculations. They're mostly average years. So there's like say 15, 20 years average. And they would still be giving you a good indication for the peak, but for the peak conditions, better to use like peak values from, let's say, ASHRAE database, or if you're in Dubai, you're going to follow what the municipality will tell you. Building envelope parameters like U values, glazing, where do you get that from? Probably the architect. You might have some conversation with them and you might guide them to go with better U values, better solar heating coefficient, better visible transparency if you're doing any daylighting, for example. Lighting layouts to get the consumption of lighting, schedule of lighting, HV system layouts, details of calculations, because you need that to input into the model. And I'm sure you've heard about that saying, and apology for the words, but it says that garbage in, garbage out. So if you put the wrong input, you're going to get the wrong output. Mind you that the model itself, as the algorithm of the software, is not perfect. There are some assumptions, there are some, let's say, simplification of what's happening and the physical, let's say, equations that we use. So the model itself, although most of them are quite accurate, but there's still some issues within the model that do not depict reality, but they're minimal compared to how we mess up as the person that's going to input that data. The data is more important than, let's say, what are the uncertainties within the model itself, because that's not quite high compared to the error that we get because of wrong input. Um, if we have any process loads, plug loads, and again, this is a bit hard to quantify, especially at design stage, even during operation, because it's just a plug, and anyone can just plug a laptop, plug a PC, uh, vacuum cleaner. So this is where you need to look at some references to figure out where you get that information from. If we have renewable energy systems, we might use the same software. We might use a different software, because at the end of the day, that's just energy production that could be done separately in a different software. Sequence of operation and control is very, very important, because that will define the schedules, how that equipment is being staged, and what is the sequence of operation of that specific equipment. Utility rates, in order to figure out what is the cost of running that building or different systems. So we start with creating the 3D model, and again, depends on some software. You might not have a 3D model; it would be just some inputs, manual inputs, and you don't need to draw the model itself. But most of the software will, and it's better to visualize the model as well, because if you're doing just the data entry and you put like the area of the window, instead of 10 square meter, you put 100. It's easy to see that on a model, right? If you have visualization, it's easy to notice, oh, there's 100 square meter window in that specific room, which should not be there. Then you would define the building envelope parameters, and that's normally coming from the architect. Internal gains, people. Where do you get that from? Probably you want to get it from the furniture layout. If you don't have that information, speak to the client, come up with some suggestions. You can look at ASHRAE Standard 6.2.1 suggestions or other references. You add equipment, lighting, so on and so forth, that are producing internal gains. Create the HV system. Is it a fan coil unit system? Is it a AHU? Is it chill beams? Then you need to define other process loads like refrigeration and others, elevators, for example. Define renewable energy system if you want to do that in the same software. Then you would perform room load sizing, system sizing, energy simulation, and you would need to review the results to see if it makes sense or not. You always need to have some sanity check on the input as well as on the output. I always tell my team that it's always good to do some sanity checks. You might have like a list and says, well, look at the area, for example, envelope area versus the GFA. it should make sense. It cannot be some numbers that do not make sense. Also, from the results point of view, what is the square meter per ton? What is the square meter or per TRH or TRH per square meter? And what is the liter per second per square meter? So you need to look at some of these outputs to figure out if that model is correct or not. Creating the 3D model, so you could import CAD layouts and then trace them over and build the model. You could also get it from BIM. So these are like some examples here. And once you do that, it is a heavy, let's say, load, depending on if you're not able to get the BIM model and you need to do that from scratch, which in some cases might be the better option. It takes time. For like a very large building, like the one on the right side, it will take time to figure out and finish that. Shading elements, if you have, let's say, some buildings next to your building and it will cause some shade in some cases, you also probably want to do that. If you have trees, for example, that are covering and helping with the shade, you want to put that as well in the software. The weather file, select appropriate weather file. The software normally would have some files. These are different weather file formats that you could use. There's one great source or resource. It's climate.onebuilding.org. They have a lot of free to download energy modeling files or weather files. There are other ones where you can create the weather file, like Meteonorm, for example. If you are in a location and you don't have any existing weather station, you could use that to produce the weather file. And typically that would have the temperature, dry bulb, wet bulb, dew point, humidity, solar radiation, wind speed, so on and so forth. Building envelope parameters, you want to look at the design and typically that would want to go with the local codes. So here you can see that for Dubai building code, this is the requirements. Now it doesn't mean that I'm going to use 0.57 in my project. The architect might have opted for 0.4, or I might have indicated to them, look, let's have a sensitivity analysis on the envelope. Let's put from 0.57 down to 0.2 and see what is the effect on the energy consumption, what is the effect on sizing of air conditioning equipment, and then we can have this feasibility study to figure out, is 0.57 the optimum or should we go lower? So that information should come from design itself. Typically, it's what the code requires if the code is already very stringent. But if you're doing a project where there are no requirements from the municipality or whoever is the authority having jurisdiction, then you would just come up with your own values and tell the client which ones are the best to use for that specific project. Now, 9.1 also have some requirements typically used for the baseline. And again, in the recent versions, the baseline is always 2004 values. If we're doing any daylight analysis, then the visible light transmittance would be required to be added because then we would be able to figure out how much of the light from the outside we get to the inside. If you don't have some data, then you can use the values from the building codes because that's going to be the minimum anyway required. If you don't have a building code, then you can start with an assumption and then figure out as you go down the line what is the U value once that is being provided by the architect. Lighting, that's going to be based on the lighting design. So if you have the lighting design, you're going to use that. And I see that a lot of this energy modeler that would just use the 90.1, which might not be applicable. And I've seen places where the values, the lighting power density, watt per square meter would be higher or lower. So you want to use what's going to be in that building, right? So what is the best decision to make now? Today I have some design from the lighting designer, and I have 90.1 recommendations or requirements, let's say, minimum requirements. Which one should I use? It might be easier to use 90.1 because just one value and just when input that, I don't need to go to the drawings and count the number of lights and check what is the light wattage per fixture. Then obviously the most accurate one is to use the lighting design. If we don't have lighting design yet, then maybe we can use the local code requirements or 90.1. Go with the local code first. If there's no local code, maybe 90.1 can give you some good suggestions. Define the control strategies. Do we have any daylight sensors? Do we have any dimming? Do we have any occupancy sensors? Add that to the software. Define the lighting gain profiles. again, that's going to be a little bit tricky in some cases because you don't have that information readily available. So you want to check with the client, what is the expected operation and schedule for that specific uh, time. Here's a list of lighting power density from the 90.1. So you can see here, this is watt per square foot. So you need to multiply that by 10, give or take, to get the watt per square meter. Now, internal loads, equipment gains, this is also going to be determined based on what's expected to be in that room. And you won't have that in, like, there's no equipment layout supplier, except if you're doing kitchen maybe. But for an office, you're going to ask the client, like, how many people are going to be there. Maybe you have the furniture layout. You're going to say, well, this is an engineering company that we're designing here, and they're going to have some a drafting team. They're going to be using some heavy PC, and you're going to go there and ASHRAE fundamentals and figure out, or other resources to figure out what is the amount of heat gain you have there and amount of energy consumption, electrical consumption. Then you're gonna go with some profiles. Again, this becomes a little bit difficult, and like what kind of profile to use for a PC. So you want to figure out that from going back to some references. 9.1 user's manual does have some recommendation on that, and these are normally are in the software as default values. You can use that if it makes sense. Again, you need to figure out, always professional judgment is required. You want to just be logical, right? So I see that sometimes the hardest thing for people to do. I don't know why, but just follow logic. Like, I have this resource, I have that resource, and that resource, let's say, is for offices in, I don't know, Hong Kong, and I have a reference for offices in Dubai. I'm going to use that one, the one in Dubai, because that kind of makes more sense. Now I'm going to look at the data as well. If the data does not make sense to me, I'm not going to use it either. So I found a report online, but it says that, in Dubai, it seems that the at 12 p.m. is the lowest amount of people there. That might not make sense for my project. So again, professional judgment, apply logic. Internal load occupancy, look at the number of occupants, the heat generated, that's going to be coming from the ASHRAE fundamentals. You can look at CIBSE Guide A as well. They're kind of the same thing. The science is science, right? It's the same thing happening, whether it's going to be in different country. The amount of heat generated from a person is going to be the same thing. So any research that was done in Denmark or in the UK or in the US or in India or in Hong Kong is going to be the same thing at the end of the day, if the research was done properly. So any reference should be okay for these kind of values. If you don't have the occupancy, maybe look at 62.1 default occupancy rates, but be very careful with that, right? Because if you look at the ASHRAE default occupancy for offices, they say 20 square meter per person. That's not going to be the case in a lot of offices here. So you're going to be not 1 per 20, maybe 1 per 10, maybe 1 per 5 square meter. So again, apply judgment, apply logic. Define the occupancy profiles. That's going to be from the client. They know the building better than anyone else. They're going to tell you the expected timing. Again, there are some default values in the software coming typically from the ASHRAE 90.1 users manual. Other gains you need to put in, you have the infiltration, and that's basically the unwanted outdoor air that comes into our building. So what are the factors that would impact infiltration rate? Would be space pressurization, envelope tightness, temperature difference between inside and outside, because whenever you have temperature difference, that will have the stack effect. You can see a photo of that, and the stack effect, that's mainly for winter. Case is going to be the opposite during summer. You have wind pressure and speed. That's going to be also, if you have a high wind hitting, let's say, the window, it's going to have more infiltration compared to lower wind speed, because that's going to create a higher pressure, and that's going to drive that infiltration more and more. That's one of the things that is not still properly done in most of the energy modeling software, because there's a lot of variances here. Some people would just use like a constant value, like 0.2 air change per hour. That's not going to be accurate, because that's not going to happen at all times. In some cases, depending on the wind direction, you might have exfiltration in one room, and some other hour would be infiltration. And we do that. Let's say I as can, if you put the amount of, let's say, holes in the walls, and the sizes. And again, where do you get that from? Building is not built yet. I cannot do a test to figure that out. Even if I do the test, I wouldn't know like exactly where every crack is in the wall, but does give me kind of a good indication of the amount of cracks in the whole envelope. So as you can see, a lot of different factors to consider, and one of the toughest, let's say, parameters to look into and to figure out, like what is the amount of infiltration, because of all these different things. How tight it is, I don't know. I could assume something and hope that it will happen in the future. But I said, even if you have the testing done, you wouldn't know exactly what that crack is and on what wall and what orientation. So again, it's a little bit difficult to do infiltration. And some people will consider zero infiltration if the building is pressurized. Don't think that's correct. So you will have to do something about it. So you can assume what is the, let's say here, Dubai code says it should be not exceed 5 cubic meters per hour per square meter. You can use that value to figure out what is the crack size, and then input that into the software, input the weather file where it has the hourly wind speed and wind direction. You have the outdoor temperature, indoor temperature that you can consider the stack effect, or that's what the software will do. And it will have kind of an hourly infiltration rate per room. That's more computation time. Some people will say, oh, let's just assume 0.2 air change per hour. That does seem sane. Let's do that and cut to the chase and figure out what is the consumption due to the infiltration. You can do that. But again, figure out what you're trying to achieve in your building, and the choice is yours. Ventilation rates in our region, we follow ASHRAE standard 62.1 for commercial buildings, ASHRAE standard 62.2 for residential buildings, and we can go back to that standard. In most of the energy modeling software, these values would be already embedded within the software, so you can choose the type of room, and then you can check what is the ventilation. However, ventilation is not only the volume you get to the breathing zone, you need to look at the air distribution effectiveness. You're going to look at the system efficiency, and these might not be readily available within the software, and you will not be able to figure that out unless you look at the actual design and find out what is the applicable ones from the ASHRAE standard 2.1. So if you have a seating of cold air supply, which in most of our projects that's going to be the case, then the air distribution effectiveness is equal to 1. You don't need to worry about that. But then you need to look at the system ventilation efficiency, which most of the software can calculate that for you. So again, make sure that you look into that as well. If you're doing a hospital, you're going to follow 170. If you're doing a residential, you're going to follow 62.2. Then we move into the HV system definition, and we need to define, and that's going to come from the design. So we have a chiller, water-cooled chiller. I need to define the cooling towers, the chillers, the air handling unit, the fan cooling units. What are the controls? These are control parameters. This is a screenshot coming from IAS, for example. So as you can see, a lot of different things that I need to define. I need to get from the mechanical engineer what system they're using and how they're proposing to control it. And not sure if you spoke to mechanical engineers, sometimes it might not have the answer, because the sequence operation, they say, well, that's a controls thing. That's not my thing. No, it is your thing. The mechanical engineer is the one to specify how the equipment should work. The controls engineer will take that information and put it into controls drawings and electronic drawings. So again, you need to get that information. If you don't get that information, it's hard to do the energy modeling accurately. You define the system, AHU, VAV, DX, whatever that case is. You have any heat recovery wheels. All these things need to be inside the model. And their information comes from the mechanical drawings, from the mechanical engineers, from the specs, so on and so forth. This is showing like water cooled chillers, the cooling towers. Again, you need to put the performance, what is COP of the cooling tower, what is the efficiency of that fan, efficiency of the motors on the compressors, on the cooling towers, what is the delta T on the cooling tower, what's delta T on the supply temperature of the condenser, return of the condenser, same thing from the supply chilled water return. Do I have any VFDs? What is the brake horsepower for the pump? As you can see, a lot of information. Most of that will come from the mechanical engineer. Control parameters. How are we supposed to control that? And again, some software do offer a good variety and let's say a lot of options, and you could just configure that system to work as intended by the designer. So again, there's a lot of information you need to get from the designer, and they might not even have that information. They tell you, just use whatever you think is correct. Again, this is where your judgment should come into play, and figure out what are the inputs to be inside that particular system. Renewables. If we have the software is able to do that, some of them can. We can also do that in a different tool, because that's something that related to the energy consumption. It's more related to the energy production. So you could use that inside the software is capable, which if it is, it makes sense to put it there. But sometimes you have maybe a more robust software or tools that you could use, so you can input that into the software, the separate software, figure out what is the total consumption, total production on a monthly basis, on an annual basis, and then you can, do the report for the client, let's say, and show what is the production per month, consumption per month, what is the deficit, and then on an annual case, what is the production versus consumption. Other process loads like elevators, so on and so forth, refrigeration. These might be hard to figure out, and you want to get that from some specific, let's say, uh, references and previous projects. If you've done energy audits before, and you've, let's say, looked at a large tower, you've done the measurements, you kind of figure out how much consumption would be. Or you could go to the specification of the elevator, then figure out what is the consumption of that motor, what is the expected running time of that motor, and figure that out. Exterior lighting can also refer to the actual lighting design, or you can look at 90.1 as well. So typically the energy would be coming, or the consumption would start from the loads, whether internal loads, external loads, then you go into space loads, then this will turn into the plant loads, and then you can have the economic model, which is the cost of that load. And then you have some interaction between these models. Output data. So once we get the output data, we want to probably check what is the monthly consumption, what is the annual consumption, what is the hourly consumption. Look at the EUI. If you have an office building and the resultant EUI is like 50 kilowatt hour per square meter per year, and it's not even a very efficient design, you can figure out that something's wrong in the model. If you get 1,000 kilowatt hour per square meter per year in a typical office building, that's probably not the case. We know that like in Dubai, it's going to be something between 200 and 350, for example. If we get 1,000, something wrong in the input. Look at seasonal variation. If you see like a constant consumption, could be, right? Like this case here, kind of the constant consumption for electrical. Well, why? Because it's connected to district cooling. So the cooling is a separate, uh, utility. So you can see that makes sense here. If I look at the electrical consumption, first question I would ask here, is this on district cooling? That's why we have a flat curve. Then probably that's the case. So do these checks from just make sure that the results are that make sense. Look at the end use breakdown. If I do a project in Dubai, it has its own chiller. If I find that chillers are using, let's say, less than 10%, then definitely there's something wrong in the model. So this also will give us kind of a sanity check. Look at the performance in terms of like a CO2 concentration. If you find that the CO2 is like kind of always 400 inside the building, that does not make a lot of sense. If it's modulating based on occupancy, that makes sense then. And again, if you find like something like 10,000 ppm in the room, that maybe you put too many people in there. So figure out what's wrong. Look at the temperatures. You're able to maintain thermal comfort. Well, no, I'm not going to say thermal comfort, but temperature and humidity levels. That's also something you want to look at. So you can see here temperature and humidity. Look at the performance. What is the COP of different equipment? Are they kind of making sense? If you find that COP is equal to 20, that equipment probably is not yet available in the market, probably never will be, and check that against your design to see if it makes sense or not. What is the air temperature before the wheel, after the wheel? Is the wheel configured properly? What is the on-coil, off-coil? So you need to have a lot of components. And again, depends on the software. Some of them will give you a lot of output, and you can do this, kind of dissect the information and figure out if it makes sense or not. What is the chill water flow in terms of quantity? What is the temperature, supply, return? All of these things can be checked depending on the software. But let's say here I'm looking at the IES results. You can see you can get a lot of information from the Vista Pro. Load profile, look at the load profile. Does it make sense or not? Is it peaking in summer? Or let's say if you find it's peaking in winter, something wrong input was there. Or if you don't find any much difference in terms of thermal load, then maybe you've put too much internal load, and that's basically showing mostly internal load, and maybe you see that's a small difference at night. Maybe it is the case for a data center, for example. Space gain breakdown. It's another thing you want to look at. Like if you look at the cooling load of that specific office building, people versus equipment versus lighting versus external gains, does it make sense or not? I remember I was looking at a residential building and found out that the results from that consultant was showing 70% of the load is coming from internal. That does not make a lot of sense for a residential building. So you want to do this sanity check again, figure out, even from the load distribution point of view, the cooling load, does that make sense or not? Thermal comfort, you could also do, again, if that software does have that capability, it will look at the radiant temperature, which is the surface temperature in a room, the air temperature, the air speed, the humidity, the clothing level. People, if you put them there, all they're wearing jackets and they're wearing coats inside an office, then they're going to be very comfortable at 24 degrees C probably. Look at the metabolic rate, which depends on activity level. If it's a gym, it's going to be higher than an office. The lowest will be probably a bedroom where people are sleeping, and it will show you what is the predicted mean vote, and you'll see that if you are kind of as per what ASHRAE standard 55 thermal comfort standard compliant or not. Now, last but not least, you could also do some CFD in some of the software, but that's not typically energy modeling considered. That's considered computational fluid dynamics, but some of the software are able to do that as well. And I think this brings us to the end of the presentation. I've just tried to keep us under 1 hour. And also, if you have any questions from the audience, I'm happy to answer that.
Yeah, yeah. Hi, Mr. Hassan. Thank you very much. Actually, that was quite informative. I was thinking it'd probably be just like an introduction, but this was very good, very useful for me actually currently as well, and I'm sure a lot of the others on the call found it very useful as well. I hope we can disturb you on this email you shared for any doubts in the future.
Sure.
And in line with that, we also have a small Q&A session. Actually, guys, we forgot to brief you about it. Everyone else, right before we started the meeting, we would have loved for all of you to put your questions in the Q&A chat, Q&A box, which you see after the chat on the top tab. You guys can put your questions in now. Mr. Hassan, we already have two questions from Muhammad Al Rawas. If you could just address them, yeah, we can lead the
Sure.
Q&A session right now.
Yeah, I can see that. So best way to model hot and cold aisles arrangement data center room projects. So again, that's the issue. You know, look at the software if the software is able to do that kind of modeling, because at the end of the day, we're doing a lot of assumptions in modeling. So you might want to rely then on CFD to figure out if you're getting to the required temperatures in a data center, which are important. But that's not the purpose of the energy model, right? The energy model is mainly to figure out what is the energy consumption of the equipment, and not to figure out if we are, within the range of recommended values or not. So you want to check what your software is able to do. Can it actually model hot and cold aisle? And is it even necessary to do that or not to figure out the energy consumption? So most of them will not be able to do that. You're going to just do that design and tell the software that I'm going to be using like this kind of rack unit or whatever unit I'm using, and then this is connected to a chiller, and that supply is at 20 degrees C from the chiller, and you put all that input and then figure out what is the consumption of the crack units, the chillers, the pumps, so on and so forth. But you're going to be using some other software to really figure out what is the best and optimized way to position the hot aisle and cold aisle, and the amount of air that needs to be supplied, and what kind of temperature you end up with. Are you compliant or not with the manufacturer's recommendations? So another question is recommended energy modeling software. Like I said, Equus is free and you could use that. I think it's a easy to use software. I personally used to use it maybe in 2008 or something. I don't think there's much difference in the interface, because anyway, it's an older interface. And I don't think there's going to be any updates anymore on eQuest, but you have a lot of forums that they can A lot of questions are there and answers. You could use that as well. And some, I would say, manufacturers would offer their software for free. So you could use that as well. The problem is once you want to shift to another software, then it's another learning curve. Whatever we discuss here is just agnostic from any software. So you can use whatever we've discussed here in any software. But then you need to understand where the things are in the software, what they're capable to do. So a training from the software developer would be probably needed. And again, you could use available forums. Most of these software do have that as well. I think these are the only questions I see. No, Equus is not same as OpenStudio. OpenStudio does use Energy Plus, so typically it should have better, let's say, more accurate results. Equus does use DOE. Both DOE and the Energy Plus are engines created by the Department of Energy in the US. Equus uses the older one, which is DOE. OpenStudio uses Energy Plus. There's another one, from Arjun. The problem with existing buildings is that we are not able to get all the data to model. In that case, we have to do a lot of assumption in this. Is this right way? Because again, we are adding a lot of uncertainty. So we do that a lot. So we do a lot of energy modeling for existing buildings. So we want to go to site, maybe do some measurements, figure out the airflows. So you need to put some effort on site, get that information, put it in the model. And again, why are we doing the exercise of energy modeling? Is it to figure out if I'm going to change the chillers, what kind of savings I would have? Is it going to be because I want to change the envelope? So again, you need to figure out what is the minimum information that you need to reduce the uncertainty. For example, for the chillers, I might not do an energy model. I might just do some measurements on site and figure out what is the consumption, what is the production in terms of cooling, and then check the supplier, let's say, information on the chillers and do a model just for the chillers themselves instead of doing the whole building. So again, depends on the purpose of the study. But if you want to do like a full calibrated model, then the only way is to get to site, get the nameplates, do some measurements, whether it's spot measurements for equipment that just run on a constant speed, and you need to put a data analyzer, maybe some flow meters, and collect data for maybe a week at least to get some information of what's going on. If they're chillers, maybe you need to go in summer again to figure out what is the peak consumption if you're doing your audit in winter. I have some questions from some colleagues of mine. I'll take those in turn just to keep the other ones. Any other questions?
But
So
I
Sandeep,
think
I'll,
probably
I'll I'll answer
Sa-
that question.
Sandeep's question on the unmet hours, I wanted to understand that as well. When it comes to energy modeling and unmet hours, even I have a bit of a problem understanding it, and we always just take it to our building physics team and we're like, just play around with it, give us more savings.
I mean, the unmet hours, again, it's not an energy modeling concept, right? So the unmet hours is just, are we meeting the required temperatures or thermal comfort, but it's boiled down to temperature and humidity. So are we getting what we need to be at? So let's say 24 degrees C, and how many hours during the year we're not meeting that? And again, so the rules of Appendix G, but by saying we need to be less than 300 hours, and then the difference between the baseline and these are not energy. It's not energy modeling. This is what the committee decided that it's reasonable or not. For me, I want zero unmet. If I'm doing a building for a client, I don't want any unmet hours. Why do I need any unmet hours? I want all the hours to be met. I want those meetings to happen. So yeah, that's the concept is not energy modeling. It's more of, you know, we are sizing not for peak, so we're expecting to have some hours where the temperatures are not met. That's okay from an energy modeling point of view. And again, Appendix G was created for these green building rating systems to compare. It's not to really depict reality, so it's just to compare. And they say, well, this is an issue. If I do a model and I have 2,000 unmet hours and I'm saving energy, does that make sense? No, it does not make sense, right? And I said, what is the minimum? Is it 300? I put 300. I think maybe if it's a different kind of project that is critical, maybe 300 is too much. We want to go with lower number of hours, but there has to be some rules. And for now, these are the rules that has been set. Maybe in the future, people will say, let's put it down to 50. for the baseline, and then the difference should be zero, for example, between baseline and proposed. We don't want the proposed to get more points just because they are playing with the unmet hours. I don't like that thing, like people playing around to get points.
Yeah.
We want real savings.
Yeah. I guess then that covers it. We don't have any other questions that you missed out. But yeah, I think we can wrap up the session, right, Mr. Hassan? Did you have
Yeah,
anything
yeah. I
else you
mean,
want to
if
add?
anyone has any questions, I think I've shared my email, so happy to answer that
Yeah,
over email.
yeah. But great. Thank you very much again for the session. It was really informative. We
My pleasure.
appreciate it. Yeah. And I'm guessing a few of us might be reaching out to you either by email, LinkedIn, with the questions that we've got.
Sure.
And yeah, we would really appreciate if you could like stay in touch with us and, guide us.
No problem.
Yeah. Awesome. Thank you. Thank you all for joining.
Thank you.
Thank you. Bye.
Have a nice day. Bye.
Thank you.